the next few sites, they are still somewhat important, okay, but not strictly talking about packet switching, circuit switching, and the comparison. So these sites are to answer a couple important questions. We said that packet switching, what it does is to divide data stream into small packets. But why not large packages? Right? We didn't really justify that. We kind of like that L divided by R. The time it takes to send one packet is small because this is small. And in case the link is really fast, then this is small. But if this is a little bit larger, well, not so bad either, isn't it? Well, think again. And this is the example that I try to use to set up the stage. And it's just a slightly extended version of the previous example where we have 2 hops only, just one router between the source and destination. The packet size 7.5 megabits and the link rate 1.5 megabits per second. And you see that L divided by R is 5 seconds. And because there are 3 hops, so this time store 5 seconds, 4, store 5 seconds, 4, and 5 more seconds to store. Altogether, 15 seconds to send this packet L. Now, 7.5 megabits, large, right? Sending a large package like this over this 3-hop network, 15 seconds. Let's try dividing this large message into smaller packets and see how it will work. 7.5 megabits, let's divide them into 5,000 packets. This way, each packet is only this big, 1.5K. Link rate is still what? 1.5 megabits. So to send a small packet like this, it takes only 1 millisecond. Now, look at this. This is the same network, 3 hops. Each packet is now very small. And to send one packet, the first router will take 1 millisecond to receive it and then send it out. So 1 millisecond, 2 millisecond, and only 3 milliseconds until the destination receives the first packet. And you know what? These links can work in parallel, right? Because router 1 here can be passing packet 1 while the source start passing packet 2. You are trying to do also streamlining here, except that the unit of the streamlining is a small packet. You see, why packet switching suggests small packets? Because it's trying to maintain the benefit of doing circuit switching. Unfortunately, we could not be streamlining bits, okay? But let's keep the packet small. Then we get to keep some of these nice properties in a circuit switch network. And having these links that can work independently is nice. We can pipeline or streamline the sending of the packets over the network. So each link works in parallel. And the overall delay in the end is what? 5,002 milliseconds, only 5.002 seconds. If you recall earlier, if we send, okay, 5,000 small packets altogether, 7.5 megabits, each hop 5 seconds, and 3 hops 15 seconds. How much time are we saving? Big time, isn't it? This is why in packet switching, people always talk about cutting data into small packets. And why do we need to store packets first before forwarding it, right? This is one of the reasons that we still need to form packets. Why we cannot just streamline the bits. The reason has something to do with how the routers is working. So inside the router, there are 2 key functionalities, and there are 2 of these. First is routing. So there's some sort of algorithms there. The routers, given the graph of the network, computes the shortest route. At the end of it, we generate a routing table like this, a forwarding table like this. And the way we look up this table is by matching the destination address, okay, of the packet. And so if a packet comes into a router, inside the router takes the destination address in the packet and look up this table. If there's a matching entry, the router discover what is the next router to forward to, what is the right direction to pass this packet further. Okay, you see, router what? Oftentimes well connected to other routers on the internet. So this router here could have multiple ways of passing the packets further. Unlike the very simple scenario there, each router has only one outgoing link, right? So it's no longer that intuitive why packets need to be stored and then forward. Now you see, packets need to be stored here, and then the router can look up this field and match this entry and then discover, okay, this packet is supposed to go out on network interface 2, this direction, to this router next. Similarly, this router needs to store the packet entirely, and then it can look at the header, this particular field, destination address, and find out in its own routing table which router next to forward the packet. Yeah, it's exactly because of the forwarding functionality that's required to pass data around over a packet switch network like internet. So on packet switch network, we store packet before we forward it. So forwarding here is to move packets to routers all the way from the source, eventually reaching the destination. Right? We'll definitely tell you more as we come to chapter 5. Okay. So in datagram network or in data network, the way it works is let's receive a packet entirely, okay, and look up the destination address to determine which is the next hop. And so you see, if the routing table change, if the graph change, routing table would change. When the routing table change, when the forwarding table change, yeah, the subsequent packets might be following a slightly different path to the destination. Okay? So the routes, packet traverse might change in a session, in a data stream session. So the analogy here is that packet switch network is a little bit more like the regular car network. Okay, if we are driving a car, a lot of times, hey, to find out the next segment, okay, which road segments we should go on, we might actually stop and pause and ask someone for this destination, for direction, or park to the side and then look up Google Map to find out which is the next segment. Right. And actually in a packet switch network such as internet, we can potentially emulate a circuit-like behavior that is called virtual circuit network. So instead of looking at the destination field in the packet header, we look at a very special header field called the virtual circuit ID field. Okay, so there's a tag there, carries a number. Okay, that number determines which is the next hop. So inside a packet, there could be many fields in the packet header. One is called destination. There's another one called the virtual circuit ID. And one can look up that field and decide which is the next hop. And how do we do that? We'll talk about that also in chapter 4 and chapter 5. And what's nice about this approach is that we can then try to ensure, okay, all the packets for that stream traverse a fixed path. In a way, packet number 1, 2, 3, 4, chances high that they arrive in order. In this case, in case routes might change, if the later route is shorter than the earlier route, chances there packet 1 might arrive after after packet 2. So, packet switch network. To sum everything up, this is general communication network. 2 different flavors depending on which philosophy we design the core of the network. If we are going for a circuit core, it's called circuit switch network. If you are going for a packet-centric core, packet switch network. In circuit switch network, we know there are different ways of dividing resources into pieces. Frequency division or time division. But either way, it's very regular following certain order. Things will need to be reserved. There's a call setup delay. It's good for long-lasting calls where you will prefer data not experiencing variation in delay, not experiencing losses. But this is very resource consuming. Each time we will not be able to allow many users going on at the same time. On the other hand, packet switch network, simpler, flexible, no idle resource, but we might have congestion. So that's this track, datagram network. We look to the destination network address and then decide which is the next hop to forward. And so we need to store the entire packet, and so they might get queued. And they might get dropped in case there's not enough space in the queue. But we can also try to emulate a circuit behavior using the virtual circuit tag, which allow us to look up into the packet header field that's a little bit faster and streamline the process more or less and maintain packet arrive orders. Packet switching versus circuit switching.